Last but not least, there's one other perk that comes with, if I can get my scroll wheel to cooperate, we can get another perk out of one of these solvers. They not only solve differential equations, they also do some extra stuff as well. So we're going to take a look at the bells and whistles that these solvers come with. The motivation being, of course, if we look at our simulation code, so when we say ODE 45, please solve for me this differential equation f from 0 to 10 for first 10 seconds and some initial condition. This is your time span, right? So let's take a look at the roller coaster problem where you've got some track, and once you hit the end of the track, things change. There's a fundamental difference in the behavior after you hit the end of the track. You're not on the track anymore, so the rules change. What's the problem with just trying to change your inputs so that you stop when the track ends?
Your roller coaster might change over time, might redesign it.
Absolutely. Your roller coaster, you have to specify the time, and if you change your roller coaster, it takes you a different amount of time, then you have to figure out what that time was, how long does it take to reach the end of the track, and it's not going to be that accurate either. Whatever you do is going to be plus or minus 0.1 seconds. You'd actually could be modeling a little bit on either side. Time is not the right thing to compare, is really what it boils down to. The simulation time should not define when you hit the end of the track. Hitting the end of the track should define hitting the end of the track. And so what we need to do is to have the solver, as it's simulating, remember, all this would do is predict motion ahead over little time intervals. And what we want it to do is just ask itself, as it gets towards the end here, it's going to ask itself all the time, but ask itself, hey, is my x-coordinate bigger than something? Bigger than, so I'd have to give it some number, like, say, 5 meters here. Is x bigger than 5? If x is bigger than 5, I've gone too far. I should back off a little bit and let the solver take care of that calculation for you. So you can imagine adding an if in our solver, which, okay, delta t, do a loop, take a step, take a step, take a step. In each of those steps, is x greater than 5? No? Keep going. Is x greater than 5? Keep going. No. And then the last one, hey, x is greater than 5. I just predicted myself past the end of the track. Okay, let's shrink the time intervals. Let's adapt the time intervals until we end up as close to the end of the track as we care to get, like a few decimal digits of accuracy there. So that is what we would like it to do. And fortunately, MATLAB has those kinds of tools built in already. So this is an extra, though. So where we find it identified in the help menus is under the ODE set, which sets the options for differential equation solvers. So we're going to scroll up to the top here. No, we're not. We're going to find the search. And we're going to look for ODE set this time, which is create or alter options for differential equation solvers. Perfect. And hello, there we go. Step size properties, solver output properties, error control. Those are all potentially interesting, but they're just about how well it fits a particular problem. The event location is what we're looking for. Now, this is going to be a little bit abstract in terms of how it's implemented. The concept is exactly what I mentioned, though. Every time it tries to take a step, it's going to ask first, do I end up past some condition or not past some condition? And that'll influence what happens. I'm just going to take a look at this one here. So one of the classic examples of where you would model with this kind of event is I drop a ball. The physics is really straightforward, right? Acceleration due to gravity until the event of hitting the ground occurs. So actually, they threw it up in the air first. And then it bounces, and then it hits the ground. Then you have to do something and then have it bounce again. So this is another way to think about it. When would I use this kind of event detecting technology? When something interrupts the natural flow of the simulation. Same thing with the end of the track. The end of the track happens, something should stop at that moment. So what we're going to do here is take a quick look at the help again here and see what it says. We are going to have to create a function. All right? So we're going to create a new function. And this is, again, a very common structure in mathematical numerical programming, so it's not like this is a weird thing. It's weird the first time, but it's not weird overall. You'll see it a lot. The idea is we're going to hand 3 numbers back. We're going to write a function that does that comparison for us. And notice what it has as inputs? T and Y. Inputs are T and Y. So this is asking what time is it and what's the current state. And it's going to return a value Through zeros, there we go. Kind of like, very similar in spirit to why we set up zero root finding things when we did nonlinear solvers. We made every equation be a function equals 0. It's going to be the same thing here. When the value our function gives back is a 0, that means something happened. So that's going to be our model. We're going to want to return a 0 when something happens. And we'll see how this plays out. It's easier to see with the example. And we're going to take as our example someone building a brick wall on our spring system. So we've got our spring. It's stretched out. And then we're going to build a brick wall right here at x equals 0. So it's going to smack into it and stop. So that's what we're going to imagine here. What we're going to need as a building block is the events func file. Events func. So we'll just grab that and put it into MATLAB. New file. There we go. Events func. Yes, I do. All right. So this is a slightly expanded version of what they give as an example. They had just t and y. We have t and w because we have position and velocity. And a threshold. What I've added is a threshold here. And the idea is I would like to stop when my x equals 0. Okay? I'll stop when x equals 0. That's actually really easy to write out. It's already in the right form. But I have to remember that x is w1. X is my position, and I remember that x prime was w2. So what we're going to do is ask, hey, is x equal 1? Is x equal to 0? Is x equal to 0? Is x equal to 0? We're going to ask it in w1 form. But that's all we need to do. So in fact, let's get rid of this for a second. It'll play a role later, but not right now. So the idea is we're going to give back this function a value. Someone tells us what state it is. Our state is going to start at 4. So for concreteness, our position is 4. So the first time we hit this function, it's going to be at x is 4. W1 is 4. Then W, it's going to be 3.9, 3.8, 3.7, 3.6, 3. And you can feel those are all positive numbers. The solver is going to stop when value equals 0. So it's going to stop when x reaches 0, or when W1, which is our x position, reaches 0. We just need to incorporate that into our solver. So we're going to save this as a new script here, W94. Get rid of all the junk about ODE Hoynes. We don't need that anymore. We'll just use ODE 45. That's fine. But we're going to add these options. Let's go back to the syntax here. Sorry. ODE has names and events. There we go. Event location property. There we go. So the string we have to put in is events. All right. So we have to put the string in events, and I'm going to call it EV here. All right. So very much like this spring differential equation had 5 inputs, but the differential equation only knows about functions with 2, t and w. The same thing, the events function. Mine currently has 3 inputs, tw and a threshold, tw and threshold, but the solver only will accept things with 2 variables in it. So we use exactly the same little shortcut, create a new name for the same function where it maps to what we wrote with t, w, and our threshold. And we'll put the threshold up here, equals 0 for now. All right. So the logical blocks are those 3 lines go together, then we simulate, then we plot. We'll run this. And it's supposed to have hit a brick wall here. It did not. There's a very good reason for that. We didn't add the options. We created this lovely structure called options, but ODE 45 only knows what you give it. And you have to provide it with those options, otherwise it will not use them. That is exactly the answer. We add it to the end, and now, look at that. It's simulated until some event occurred, and the event was us hitting x equals 0. So if you zoom in on this point here, it'll be very, very close to x equals 0. Yeah. It won't be perfect. There'll be some round-off error. We can also see this in our t and w. I'll do that same stacking someone just asked for before. Well, that's T2. Sorry, T2 is our new one. T2 and W2. So our simulation, and here's where we get the time. The time is some very odd time. How long does it take to go back to 0? Well, I don't know. It takes 0.9068 seconds, apparently, with some more digits. And it takes us very, very close to that 0 value. If we actually look at the end value in column 1, it'll be W2, sorry. It's not 0 exactly, but it's very, very close to 0. 10 to the minus 15, pretty close. Let me pause there for questions or comments before we tweak this and experiment some more.
Does that only happen at x equals 0? Can you do it for any arbitrary value?
Absolutely. So the idea is, what about some other value? So what if we wanted it to stop at x equals -2, for example? So here we have to say, what we need to have it stop is when a value equals 0. So how can I go from I want to stop when x equals -2 to something equals 0? What would equal 0? Exactly. Move the 2 over to the left-hand side, exactly like we did earlier this term. Hey, my value is going to be x plus 2, or better yet, x minus -2. So that idea of capturing, I want to stop at some random point, or say, hypothetically, if you're doing the roller coaster, I'd like to stop at 5 meters of track when my x reaches the end of the track. Well, then we just rearrange this, and I'm going to stop when x minus my value, we're going to call it threshold, the stopping value here, when that equals 0. And if we look at the code in events func, that's exactly what we had in there. There was a minus threshold here. So the value will be computed as x minus our target. When that hits 0, then x equals my target. It's that just rearranging the equation so all the numbers are on the left, and we have a 0 on the right. But if we try that, I close this window, we should see the simulation stop when x equals -2 now. So go back to our main script, run it, and I didn't change the threshold, right? I put the threshold back in, but I didn't set it. Thank you. So threshold is now -2, so we should stop when x equals -2, or x minus -2 is 0, and that's exactly what we get. Perfect. Right. So we can stop at -1. We can stop whenever we want in terms of x coordinates there. This is a trickier one, though. Let's go one step further. If you understand that first part, you'll make that even more solid. If I want to stop at the first bottom swing thing, what's the obvious thing to stop at? X equals? That's right. That's the right way to do it. So the naive way would be to say, I want to stop when x equals -4. All right? Now, the problem with that is, as we saw, we only get dots. We only get dot simulation. And we barely reach 4, and then we don't quite get away. We can try it. Let me just try it for the sake of argument here. If I set the threshold to -4, it actually does not stop, because the solver never actually goes through 4. It never goes beyond 4, which is good, because that would mean we were gaining energy, and that would be weird. But it means that we can't stop at that point because we never cross into things beyond 4. But your point about the derivative being 0 there is perfect. How would I find or check whether the derivative equals 0? What would I test there? Velocity equals 0, and where's that hiding in my inputs? W2, exactly. So if you say, and you have to change this, there's no real nice way to make this general, but if we make our threshold 0 now, but we're now testing the velocity, this is perfect. It stops it exactly at the bottom of the cycle. So between position and velocity, between the variables that are available to you, you should be able to stop at some interesting points. That's what this boils down to.